Hello everyone. Thank you for joining. My name is Naresh Kumar Reddy Yelkoti, and I'm currently a senior cloud and application security engineer. Over the past decade, I've been deeply involved in securing enterprise scale systems across AWS, Azure, and GCP, with a focus on integrating security directly into the development and deployment process, what we now call DevSecOps. I worked on building and implementing security pipelines that perform compliance checks, vulnerability scanning, and real time threat detection for everything from traditional applications to modern serverless workloads like AWS, Lambda, and Azure functions. I have led migrations from traditional security platforms like Prisma Cloud to more advanced solutions like Visio, closing gaps in container and serverless security. I have designed CI/CD integrations that block insecure builds before they reach production, combining tools like VCLI, Fortify, and AWS Inspector. I'm also involved in API security with NeoSec, defining sensitive data handling strategies and onboarding PCI and non-PCI workloads for continuous monitoring. Today's talk, building memory safe DevSecOps at enterprise scale, is about a challenge I've seen repeatedly. Over the years, I've seen a recurring challenge. Many security tools themselves are written in memory unsafe languages like C, C++, which means that tools designed to protect us can introduce new vulnerabilities. That's what led me to explore Rust, a language that eliminates entire categories of memory safety issues at compile time. Today, I want to share with you how Rust memory safety, performance, integration, flexibility can help us build safe security tools we can trust, and how we can practically bring Rust into our existing security pipelines without starting from scratch. So that's a bit about who I am and why this topic matters to me. Let's take a quick look at what we will cover today, and so you know exactly what we are headed. Here's what we will cover. First, we will look at Rust's memory safety advantage, how its ownership model eliminates entire classes of vulnerabilities, leading to up to 40% fewer security incidents. Next, we will explore technical implementations, real-world examples like static analysis tools that block insecure code before it compiles, lightning-fast container scanners, cryptographic pipelines that stop supply chain attacks, and memory-safe policy engines. Then we will review performance benchmarks showing how Rust tools can run 10x faster than Go or Python language using 60% less memory, with examples from Cloudflare, Dropbox, and Discord. Finally, we will discover integration strategies so you can bring Rust into your DevOps workflows, whether it's a gate hooks, Kubernetes administration controllers, or API gateways, without major disruptions. Before we dive into Rust, let's first understand the problem we are solving, the memory safety crisis that's affecting almost every modern systems. The memory safety crisis from memory safety flaws are still top cause of critical security issues. Microsoft reports that 70% of its CVEs come from memory safety bugs. Problems like use after free, buffer overflows, data races plague C like C++, because developers have to manually manage memory. Traditional scanners detect these only after code is written, and runtime monitoring can slow down applications here. For examples, in a real-world case, a buffer flow in a C++-based API gateway allowed attackers to overwrite session data, gaining admin-level access. This is issues that cost millions to fix and damages trust, and it's exactly the type of risk Rust is designed to prevent. Now that we know the scale of the problem, here's what Rust changes the game. It makes the whole categories of these vulnerabilities impossible by design. Rust memory safety guarantees. Rust changes the game by making entire categories of vulnerabilities impossible at compile time. It enforces ownership, so every piece of data has only one owner. no double freeze, borrowing rules unsafe, ensures safe reads and writes without corrupting memory. Lifetime make sure nothing outlives its valid scope, and fearless concurrency means no data races even in multi-threaded code. If you build a container scanner or an API gateway in Rust, you are not just protecting applications, you are ensuring the tool itself is not a new attack vector. This is why companies like Dropbox have reported zero memory safety bugs in Rust-based modules. And this is not just theory. When organizations switch to Rust, they see real-world results. Let's talk about the measurable impact it's having. Enterprise impacts. The number speaks for themselves. Enterprise migrating critical components from C++ to Rust have seen a 40% drop in security incidents. Properly written Rust code has zero memory safety bugs. Static analysis tools in Rust can reach 95% detection accuracy with fewer false positives, meaning security teams spend less time chasing more noise and more time fixing real issues. For example, when a financial services firm I worked with saw their vulnerability backlog drop by 30% in 3 months after introducing Rust-based scanning tools. So how do we actually put Rust to work? Let's start with the static analysis, catching unsafe code practice patterns before they ever reach production. Static analysis tooling, Rust parsing libraries like Sin and ProcMark2, make it perfect for building static analysis tools. You can scan code at a compile time, spot SQL injections patterns, and block insecure commits before they hit the repo. Compared to Go-based scanners, Rust tools run 3 times faster. And compared to Python-based tools, they are 10 times more reliable. In a security pipeline, that means you can scan huge code base in seconds without bottlenecks. Imagine a CI build that rejects a vulnerable API endpoint before it even deploys. Static analysis protects code before it's built. But what about the things we package and ship? That's where container scanning comes in. Rust really shines there. What is container? Let's start from the basics. A container is a lightweight, portable package that includes an application and everything it needs to run the code, libraries, runtime, environment variables, and configuration files. Think of it as a shipping container for software. It does not matter if the ship is AWS, Azure, GCP, or on-prem. The container runs the same way. Docker and Kubernetes have made the containers the backbone of modern application deployment. The benefit: containers are fast to start, easy to replicate, and scalable. But the flip side is, if you package vulnerabilities inside your container, you are scaling those vulnerabilities everywhere. Why containers need security scanning? A typical container image can make up dozens of layers, often pulled from public repositories. This means you are potentially inheriting vulnerabilities from someone else's code. Common container risks include outdated base images using Ubuntu or 16 version or that's reached end of life, and embedded secrets like API keys, passwords left in some environment variables, vulnerable libraries like Log4j, everyone knows that, and or OpenSSL, misconfigurations, insecure file permissions, etc. Real world example: in 2021, attackers compromised Kubernetes clusters by exploiting containers running outdated Alpine Linux images. That's why scanning containers before deployment is non-negotiable. How traditionally scanning works. Traditionally, scanners parse the container, extract the file system's layers, and compare and install packages against known vulnerabilities databases like NVD or vendor advisors. The problem with some existing tools, performance bottlenecks, Scanning hundreds of images can take hours. Memory leaks, scanners written in unsafe languages can themselves be exploited. False positives, noisy results, that wastes security team time. In CSCD, slow or unreliable scans lead to a tough trade-off, speed versus security, and then that's where Rust gives us a breakthrough. Coming to Rust-based container scanning, Rust is designed let us build container scanners that are fast, safe, and accurate. The improvements Rust brings are like zero copy parsing, parallel scanning, async reporting, zero copy parsing with creates like bytes. The scanners can read container layers directly from disk without duplicating data in memory. This means faster performance and no unnecessary memory use. Parallel scanning using Orion, or we can scan 10,000 plus images per minute without breaking a speed. Async reporting libraries like Tokyo let us send scan results to dashboards or security tools without blocking the scanner process. End-to-end, let's walk through end-to-end use case in DevSecOps pipeline. Developer pushes code that triggers the build pipeline. Docker image build, a base image plus an application code or packaged into a container, and then Rust-based scanner runs. Before the image pushed into the registry, the scanner analyzes each layer, checks installed packages against CVE databases, flags outdated OS components or insecure configurations, detects secrets left in code or environment variables, and scan results evaluated. If critical vulnerabilities are found, the pipeline blocks the deployment and sends results to however integration has happened. It may be ServiceNow or Slack or Zeta. Image push to registry only if clean, ensuring production gets only safe, verified containers by embedding the Rust scanner here. You are shifting security left, stopping vulnerability before they ever touch production. So in short, containers are powerful, but without scanning, they are high-speed delivery systems for vulnerabilities. Speed is great, but trust is non-negotiable. A scanner written in a memory unsafe language can be exploited via the very images it inspects. Rust memory model makes entire classes of parser and concurrency bugs impossible by design. So that tools is not a new attack surface. Rust lets us build scanners that are both faster, safer than traditional tools, making it possible to secure containerized applications at enterprise scale without slowing in innovation. Now we have scanned the container vulnerabilities, but how do we ensure no one has tampered with it between build and deploy? That's where cryptographic validation steps in. Cryptographic pipeline validation. Supply chain attacks are on the rise, so verifying your build artifacts is critical. Rust, Ring, and results libraries give you memory-safe cryptographic methods, avoiding the pitfalls of C-based OpenSSL. You can sign and verify artifacts without unnecessary data copies, reducing the risk of time of check to time of use attacks. Discord implemented a Rust-based cryptographic verification and saw a 100% drop in certain supply chain attacks attempts. And finally, even within the secure images, we need to control what runs in your environment. Let's see how Rust can power memory-safe policy engines. Policy engines decide what's allowed in your systems, and if they are compromised, you are in trouble. With Rust, you can compile policies on WebAssembly, offer sandbox executions, or ensuring they run safely across platforms. You can validate configurations without risking buffer overflows or even hot swap policies without restarts. For example, in Kubernetes, you could enforce that only signed images are deployed and updated the policy instantly without downtime. We have seen the technical side. Now let's talk numbers. How much faster, safer, and more efficient are Rust-based tools compared to traditional ones? If you look at the slide here across real deployments at Dropbox, Discord, and Cloudflare. Rust-based tools can move faster, use less memory, and produce fewer false positives than Go or Python equivalents. In numbers, 3 to 10 times faster scans, 60% less memory use, lower false positive rates, all without sacrificing safety. That's the definition of security at scale. Of course, none of this matters if it's too hard to adapt. The good news is you can integrate Rust-based tools into your workflows without major risk. Integration strategies. You don't have to rewrite your stack to benefit from Rust. You can integrate it gradually, pre-commit hooks to block bad code, add GitLab CI jobs, and automated scanning to various admission controllers for runtime policy enforcement, and API gateway middleware for live request validation. Key takeaways: Rust eliminates entire classes of vulnerabilities at compile time. It delivers faster performance, lower memory use, and higher detection accuracy than traditional tools. You can start small, dependency scanning with Cargo, audit container scanning with Rust-based tools, and grow from there. The future of secure infrastructure is not just better detection, it's making certain vulnerabilities impossible. Rust delivers on that promise. Thank you.